Perfect. All right, so this is going to be the last problem of section 4 and as much of section 5 as we get through today. So if you don't remember what we've been doing, so the first section of chapter 5 was about Pythagorean identity. It was the reciprocal identity, so all the reciprocal functions. It was the quotient identity, so how can you rewrite cotangent and tangent in terms of sine and cosine? Then in section 3, we said, okay, what about solving, right? We're treating, like we have these big equations and we try to solve for what angles make it true. And section 4 is what if I'm adding or subtracting two angles together, etc., etc. So the big one for section 4 is the sum and difference identities. So you're literally adding two angles together or you're subtracting them. And this is useful when you're trying to find sine, cosine, tangent of an angle that you don't know. If it's possible that you can rewrite it in terms of two angles you do know, 30, 45, 60, 90, 0, multiples of them, then this is really useful. Okay, let's go down here. It says solve cosine of pi over 3 plus x plus cosine pi over 3 minus x equals 1/2 over the interval of 0 to 2 pi. So this problem puts together both section 3 and section 4. So section 3 is solving. Here we have an interval, so we don't have to do plus 2 pi n because it's only between 0 and 2 pi. But here I'm adding, and I'm subtracting angles, so that's section 4. So what we have to do is we have to apply an identity twice. We have to apply the sum identity for cosine, and we have to apply the difference identity for cosine. Okay, so I'm going to try to just going to color code the first line. I'm going to make it really different. Okay, so this first one, we see this is cosine of alpha plus beta. I'm literally adding two angles together. So this is going to be the same as cosine pi over 3 cosine x. Let's see, minus sine pi over 3 sine x. And then I have this one right here. Let me know if the color is not contrasting enough. Try and divide it up. Cosine of pi over 3 minus x. Okay, so I'm going to rewrite this using the difference identity for cosine. So this is going to be cosine pi over 3 times cosine x, and then it's plus sine pi over 3 sine x. And don't forget to write equals 1/2. All I did was I rewrote this whole line right here, just expanded each one of those out. And now let's see if we can combine any like terms. Is there anything that we could? Maybe not. Okay, let's chill. Let's go through. What is cosine of pi over 3? Cosine pi over 3 is cosine 60. Cosine of 60 degrees. Let's see if this is 60, this is 30, 1/2 root 3 over 2. So if I want cosine 60 degrees, it would be 1/2. So I have 1/2 cosine x minus what sine of pi over 3? Sine of 60, root 3 over 2, root 3 over 2, sine x, plus, well, we already know cosine of pi over 3 is 1/2 cosine x. Let's see, plus root 3 over 2 sine x equals 1/2. All I did was I input root 3 over 2 for sine of pi over 3. Okay, so don't say it out loud. Think in your head. No mouths. What would be the next thing you do? What do you recommend doing? Maybe look for anything that cancels, turn to the person next to you. You'll have a partner. What's the next step? What do you think the next 2 steps would be? What's the next 2 steps? Just like, all right, Jolie, say it a little louder.
Cancel it out.
Cancel it out. Check out, I have negative root 3 over 2 sine x, and I have positive. Wait, those cancel out. Also, if I have half cosine x plus half cosine x, what's this equal to? 1. So literally, I'm just going to have cosine x equals 1/2. Beautiful. So now I'm asking myself, where is cosine equal to 1/2? So literally, when I say where is cosine equal to 1/2, what I'm doing is saying cosine inverse of 1/2 is equal to x. I'm looking for the angle where cosine is a half. Which angle is this? Let's see. So there's going to be two places where tangent is positive. Where cosine is positive and it will be equal half. So we know that this is 60 and this would be like negative 60. Like, what's another way to say this angle? What if I go all the way around? So this is pi over 3. This would be 5 pi over 3. Okay, cool. So we just say x equals pi over 3 and 5 pi over 3. So this is very similar to what we've been doing with section 3. Difference is we just use the sum and difference identity to expand it out. Maybe something will cancel. Maybe something adds together. Yeah, and then that's it. That's maybe I should have finished it last class. Do you have questions over this one? Groovy. Okay, let's keep going. So, section 5. These are where, I don't know if these are the hardest identities. I'm glad we're going to have lots of days to review because we need to practice. Literally the hardest part, it's not actually applying the identity. It's literally figuring out which one to use. It's not necessarily like doing the identity. It's figuring out which one to actually use. Because when you look at a problem, you're like, I don't know. Is there any like tricks? Are there any tips? Like, how do I know which identity and specifically to use? So I'll try to be specific as we go through, but on the review day, like, that's when I'm really going to try to distinguish it for you. But first I have to like tell you about them. So section 5 is multiple angle and product to sum identities. So a couple of things to note. All right, so just some like basic algebra. If I would have sine of x and I'm adding sine of x, what is this equivalent to? 2 sine x. Okay, I'm really not trying to trick you. I'm just trying to make sure we're all on the same page. What about if I have like, what if I do like sine of 50 degrees plus sine of 50 degrees? What does that equal to? But wait, you just told me sine x plus sine x is 2 times sine x. So sine 50 plus sine 50 is going to be 2 times sine 50 degrees. So you can't just add the degrees inside. Trick. Well, that time was a trick. Okay. What if I say sine of x plus x? What is this equivalent to? Sine of 2x. Excellent. And what if I say, this is going to be a dumb one, just to make sure you understand that. Sine of 50 degrees plus 50. This time is when we will actually add them. So I'm distinguishing when you are adding sine of an angle plus sine of an angle versus sine of the addition of the two angles. So if you are adding outside the angle versus like inside the parentheses, that's a difference. Okay. So section 5 is multiple angle and product to sum identities. So what if you have like multiples of an angle or multiplying two angles together? I guess you'll see. Okay, so double angle identities is kind of what we just talked about. So what if you have like sine of 100 degrees, right? Well, that's equal to sine of 50 plus 50. So this sine of 2 theta here is just 2 times whatever angle you're putting in place. So this is the double angle. So let's say we have, trying to think of a good example. Sine of, well, I could do like sine of 60. If I do sine of 60, well, this is my double angle. 60 is 2 times what my theta is. What would my theta here be? 30. So, I mean, not the most useful because we know what all the 60-degree angles are. But this would be equivalent to sine of 60. Similarly, if I do tangent of 60, it would be the same as 2 times tan 30 over 1 minus tan squared 30. So these are double angle identities. So notice for sine, you have one choice. Tangent, you have one choice. But for cosine, you have 3 choices of what you can use. Does everyone see this on your equation identity sheet? Okay, just making sure you're familiar with where it is located. All right, so also cool thing, if you know sine of 2 theta and cosine 2 theta, you also can figure out tan of 2 theta by doing the regular tangent is equal to sine over cosine. So technically, tangent has 2 options of how you can solve, but this is only true if you know what sine of your double angle and what cosine of your double angle are already. Okay, let's go on, let's do this first example, because this is a lot of sounds like nonsense. If sine of theta is 3/4 on the interval 0 to 2 pi, find sine of 2 theta, cosine 2 theta, and tangent 2 theta. We're looking for the double angle identities. All right, so the first thing I want to do, well, let's look. I want to find sine of 2 theta, but in order to find sine of 2 theta, I have to know sine and cosine. Right now, I only know sine. How can I find cosine if I have sine? Beautiful. That was wonderful. Let's get a little point for that. On the ball. I don't know. Is that not fair? Whatever.
I'll take the point.
Yeah. Cool. Cool. So we're going to use Pythagorean theorem. So whenever you have sine and you're looking for cosine, the easiest thing to do is use the Pythagorean identity. So we're using it from section 1. We're going to get cosine and cool. So we know sine squared theta plus cosine squared theta is equal to 1. And I know sine is 3/4. 3/4 squared plus cosine squared theta is equal to 1. So of course, 3 squared is 9, 4 squared is 16, plus cosine squared theta is 1. So subtract 9/16 from both sides. So 1 is the same thing as 16/16, right? What's 16 minus 9? 7, okay. So all I did was I subtracted 9/16 from both sides. Technically, this is 16 over 16, so 16 minus 9 is 7/16. Cool, just for clarity. All right, so now I have cosine squared is equal to 7/16. I need to square root both sides. So I see that cosine of theta will be square root 7 over 4. Plus, minus, let's see, do I need to... How can I justify why we only need the plus 1? Let me think about this for a sec. So because I only want the plus 1, so normally, you're right, you do have a plus minus. I only want the plus. Let's see, why do I want only the plus? Because your SIGN, your plus negative, you look at what angle you have, and that determines whether it will be positive or negative based on the terminal, based on the quadrant. Right, that's a sufficient explanation. So the reason I'm just going to take the plus 1 is your plus or minus comes from the quadrant at the end, where double angle lies. I don't know, wherever it lives, whatever quadrant it hits in. That's how you can tell whether it should be a positive or negative. I'm going to take the positive, and I'll figure out the SIGN plus negative at the end. Okay, so I know I'm just going to leave the positive one. All right, so I have cosine, I have sine, and the first thing we have to do is find sine of my double angle. That's just going to be equal to 2 times sine theta cosine theta. So this is just going to be 2 times 3/4 times square root 7 over 4. And if I simplify, both these are divisible by 2. So I have 3 root 7 over 8.
Why'd you get rid of the sign?
So I plugged in. I know sine of theta is 3/4. I know cosine theta is square root 7 over 4.
Oh.
Try to solve. Finding cosine of my double angle. Which one would you like to use? The first one? Okay, cosine squared minus sine squared. Oh my gosh, you have me go and square them? I mean, I could.
Well, but because we already have them.
You're right. Okay. Okay, cool. I'll do that. Good point. All right, cosine squared theta minus sine squared theta. So that's the first one up here. All right, it just says we already have it squared. Might as well. All right, so cosine squared is going to be 7/16. Subtracting sine squared, which is 9/16. It's going to be a negative 2/16. So that means cosine of my double angle is going to be negative 1/8. Awesome. Okay. And lastly, we have to find tangent of my double angle. I'm just going to use this easiest one right here. Cool. Because I have sine of the double angle, I have cosine of the double angle. So I know tangent of my double angle is going to be sine of my double angle over cosine of my double angle. Okay, cool. Just plugging in the two things we got. So I have 3 root 7 over 8 all over negative 1/8. 8's cancel out. Tangent of my double angle is just going to be negative 3 root 7. Perfecto. All right. Cool. Let's keep going. All right, solve cosine 2 theta minus cosine theta equals 2 on the interval 0 to 2 pi. So what we really need to do, we need to convert all of the double angles to regular angles. So instead of writing 2 theta, I need to change this so that way it's just in terms of theta. So I guess I'll write that just to be clear. Convert all double angles into single angles. So maybe, what? Nope. How do I convert cosine 2 theta? The double angle identities we just learned. Okay. So I'm looking through. The first one has a sine squared in it. The bottom one has sine squared. So I'm going to choose the second option and plug it in for my double angle. So this would be 2 cosine squared theta minus 1 minus cosine theta equals 2. So all I did was instead of saying cosine 2 theta, I used the second option that's up here. I use this guy because that way it's all in terms of cosine. Because remember from section 3, I need it all in terms of one trig function. Okay, so let's, what?
The cosine squared theta minus 1.
Yeah, but it's 2 cosine squared theta minus 1. And I don't want it to be in terms of sine because I have a cosine theta. So I want it all in terms of cosine. Yeah. Okay, let's move everything and have it on one side. I'm just going to rewrite this. 2 cosine squared theta minus cosine theta. And then I have this. I have to subtract 2 from both sides to move this over. So I have negative 1 minus 2, so that will be a negative 3 equals 0. Okay, so if I give you a problem like this, how would you solve it? Factor. So this is, this is probably not the name anyone else in the school call it. I call it the case-if method. How do you deal with coefficients in front of x squared other than 1? Moved over. So I have x squared minus x minus 6 equals 0. Oh, that's a chill one because I know it's going to be 3 and 2. The middle is smaller, so if I have minus 3 and plus 2. So what you did, since I moved the 2 over, I have to rewrite both of these as the 2x, but you see that one of them, oh, we have a common factor, I divide each of these by 2, so my 2 factors should be 2x minus 3 and x plus 1. Okay, so like I factored out this left side for myself, right? So instead of x, I'll be saying cosine. So 2 cosine x minus 3, and then I have cosine x plus 1 equals 0. Because if so in the green, right, on the right side, it's showing how you would do it in algebra 2, algebra 1, whatever. It helps us factor it out, makes it a little easier to look at. Okay, so first we converted all the double angles into single angles, moved everything, factored it, but I'm trying to solve, so I have to set each one of these factors equal to 0. So I set cosine of x plus 1 equal to 0. So I'm looking, where is cosine equal to negative 1? So really what I'm saying to you is x equals cosine inverse of negative 1. I'm asking for which angle is cosine equal to negative 1.
180.
Exactly, 180 degrees, which is pi. Cool. So that's solid. All right, now let me set the other one. Equal to 0, so I have 2 cosine x equals 3. I just add 3 on both sides. So where is cosine x equal to 3 over 2? Equal to 3 halves. So I'm asking, for what angle is cosine going to be equal to 1.5?
Never.
Never. Why?
Because it doesn't go higher than 1.
What a blessed day. It's great. Exactly. This is great. So I keep asking these questions because once you make the connections in your brain, don't worry, you can shout it out, right? Shout it out. So we know cosine and sine can never be greater than 1. What? Where's it greater? Where's it 1.5? Never. That's the answer. Never. It will never be. There's no solution, right? Cosine will never be 3 over 2. No solution. Cosine and sine can never be greater than 1. You guys graph this, you have an intrinsic idea, all right? So it always varies between negative 1 and 1. It can never be greater than 1. It never can be less than negative 1. So you bet you I will probably put a question like this on your test. Yep. I will probably put a question where I'm asking, oh, where is cosine equal to negative 2? It's not. It's never. No. Zilch. Okay. All right. And let's just make sure, do I have to add plus 2 pi n here? No, because I'm on an interval between 0 and 2 pi. I only have one answer. Done. Cool. All right, I like how there's just a sentence here. It's possible to use double angle identities to derive power-reducing identities. Yes, it's possible, but we're not doing it in this class. I'll just give it to you. There you go. Power-reducing identities. Okay, so let's say you have like a sine squared theta. I don't want it in terms of sine. How can I change it into cosine? Well, I mean, you could change it into 1 minus cosine squared, or you could write it as 1 minus cosine squared, 1 minus cosine double angle over 2. This one's pretty easy to see where it comes from. Literally, get sine squared by itself. Subtract the 1, divide by negative 2. There you go. I derived it for you. I said I wasn't, I just did. Okay, and then cosine blah blah blah. Literally, if you're trying to reduce the powers. So, I mean, it's useful if you have like squares. What if you have something like to the 4th power? I could use a power reducing identity. So I could write it in terms of, well, let me like cheat for a second. X to the 4th, this is the same thing as x squared to the 2nd power. Because when you have an exponent to an exponent, you multiply. What if I had like x to the 8th? How can I write this? X squared, squared, squared. Haha, yeah. Right? Because you multiply all the exponents together. When you have an exponent to an exponent, you multiply. Do we remember exponent rules? What if I have x squared times x to the 5th? What does this turn into? To the 7th, because you add. If you're multiplying the bases, you add. If you are literally doing an exponent to an exponent, you multiply the exponents. Okay. Cool. All right, let's go through. Yeah, and that would be the same as x to the 8th. I just rewrote it in terms of like this because, I mean, I want you to see the square with the power reducing identities. Yeah. Okay. So, example 3. Rewrite sine to the 4th theta in terms of cosines of multiple angles and with no power greater than 1. Okay, so the first thing I want to do is I want to rewrite this in terms of sine squared to some angle. Some exponent right there. Well, I just basically gave you the answer anyway. All right, we know x to the 4th is just equal to x squared squared. So what I'm going to do is I'm going to rewrite it as sine squared theta squared. Okay, wait, we know what sine squared theta is. Let's plug it in right there. Beautiful. So I'm going to have 1 minus cosine of my double angle all over 2. I put that in place of sine squared, but that has to be squared. So that means I have to multiply this, multiply this. So literally what I can do is the top one, 1 minus cosine of my double angle, times 1 minus cosine of my double angle, because the bottom is really easy to square. 2 squared is just 4. And then it is foiling it out. Gotta FOIL it out. So 1 minus 2 cosine double angle plus cosine squared of my double angle all over 4. Are we done? No, Nilch. Ah, oh my gosh, guess what it says? Okay, so it's in terms of cosine, cool. And multiple angles, yes, check. But with no power greater than 1. Well, shoot, guess what we have? Ah, cosine squared of 2 theta. So I have to come up, and I'm going to use this. Right, so that power reducing, that way I don't have exponents other than 1. Alright, you guys are gonna hate this. Nah, I won't set you up for like this. You guys will minimally enjoy it. Okay, so 1 minus 2 cosine double angle. All right, so I'm going to rewrite this guy. But wait, what angle am I plugging into this?
2 theta.
2 theta. So that means I'm doing 2 times 2 theta. If I'm plugging in the double angle. Does that make sense? So where I saw theta, I'm putting in a 2 theta. So it turns out I'll have a 4 theta. Crazy. Just trying to prep you for that. So 1 plus cosine 4 theta all over 2 all over 4. Maybe that was not clear. Okay, cosine of 2, whatever my angle was 2 theta. That way you could see why it turns into a 4 theta. Because the angle I originally had was 2 theta. Got to double it, turns into 4 theta. Okay, now is the great part where we have like a fraction inside a fraction. So we have to think of a way to like simplify this because it looks nasty, right? You got this fraction on top of ugh. So what if I multiply each of these? I'm going to multiply this by 2 over 2. So that's just multiplying by 1, right? 2 over 2 is the same thing as 1. Multiply this guy by 2 over 2. Same thing as multiplying by 1. That's why I can do it. But it helps me because now I can write 2 over 2 minus 4 cosine 2 theta over 2 plus 1 plus cosine 4 theta all over 2. All right, so what that does is it makes all of my denominators the same, and I can combine everything on top. Wonderful. Okay, just to show you, do I have room? Yes. Do I need to scroll over?
Wait.
Yeah, okay, that's chill, that's fine. Yes.
Can you only multiply the theta at all when it's directly related to zeta? Like if it was 2 theta times 2 theta. Or if it was like 2 times 2 theta, is it instead of 2?
So see over here, we're in the blue. It was like, oh, I had cosine squared of 2 theta, right? Then I was using the identity that's up above. So cosine squared of an angle is equal to this whole shenanigans. But it's 2 times whatever angle you plugged in. Since I plugged in a 2 theta into the equation up above, into the identity, well, my original angle that I plugged in was 2 theta. So now I'm doubling it instead of pi reducing.
Wait, but why did you add 2 theta? I'm so
Right here?
Yeah.
Okay. So I came out with this line right here, right? So since I can't have angles other than powers other than 1,
Right.
so I'm using this right here. But guess what? Instead of just having cosine squared of theta, I have cosine squared of 2 theta. So I'm plugging this into up here. But except, guess what? The theta is actually 2 theta. So right here, in terms of theta, I'm plugging in 2 theta in for theta.
Oh.
So 2 times 2 theta is 4 theta.
No, I'm also wondering, when you multiplied by 2 over 2, you did 2 cosine 2 theta. I mean, 4 cosine 2 theta.
Yeah.
Over 2.
So I'm multiplying the coefficient. You can't multiply inside. I'm multiplying the coefficient by 2.
And how come you didn't? Why isn't the denominator 4 on the
Why?
last one? On the 1 plus cosine
This?
4.
Oh, I didn't change it at all. What I was trying to do is change the denominator for these two. That way, common denominator. Our next step is to combine all these over one denominator. All right. So the next thing we're going to do is I'm just going to rewrite this. So I have 2 minus 4 cosine 2 theta plus 1 plus cosine 4 theta. This is all over 2, which is all over 4. I didn't really do anything, I just rewrote it in different terms. So wait, if I'm dividing by 4, it's the same thing as multiplying by the reciprocal, which is 1/4. Yeah? Nah? Maybe.
Oh, to get rid of the denominator?
Right. I'm going to write out what I verbally just said. So wait, 2 plus 1 is going to be 3.
Where do you get 2 plus 1? Oh, sorry.
It's fine. So I'm just going to combine these. That's a nice little easy combination. 3 minus 4 cosine 2 theta plus cosine 4 theta all over 2. And instead of dividing by 4 like I am right there, I can multiply by the reciprocal, which is 1/4. So that means it just turns into all over 8. Cool. So this is in terms of cosines of multiple angles, right? We have a quadruple angle and we have a double angle, and no powers greater than 1. Cool. So it's a lot of work.